Kinetic energy increases the motion of our particles, and I know I can do that by raising the temperature of our compound as well. That kinetic energy has a direct relationship to the kinetic or to the Kelvin temperature. The more motion energy the molecules have, the more freedom they can have. So the average kinetic energy is directly proportional to the Kelvin temperature. Increase the Kelvin temperature, and you increase the kinetic energy, a direct relationship. The particles are attracted to each other by electrostatic forces. That's saying that opposites attract. A positive cation with a negative anion have an electrostatic attraction. Polar molecules, such as water, where we have a region that's negative and a region that's positive, have an electrostatic attraction when opposites attract. The strength of the attractive forces varies some and are small and some are very large. The strength of the attractive forces depends upon the kinds of particles, where the stronger the attractive force between particles, the more they resist moving. Strongest particle attraction would be in solids, the least, of course, would be in a gas. No material completely lacks particle motion. Even solids, at a molecular level, solid atoms are wiggling back and forth. They have a vibrational freedom of movement. When the kinetic energy is so large it overcomes the attraction between particles, that material will turn into a gas. In an ideal gas, the particles have complete freedom of motion, especially translational freedom. They have complete freedom to move around, occupying the container. Ideal gases then expand to fill their container and are said to flow. Because they have very large spaces between the particles, they have very low density and high compressibility. Gas molecules are in rapid, constant motion, moving in a straight line until they hit something else and complete their change of pathway. A random walk is what we defined that term. A molecule will travel in a straight line until it hits something, and then it will ricochet, travel in a straight line until it hits something, and continue in that pathway. So gas structure, complete freedom of movement. When the attractive forces are strong enough so the kinetic energy cannot overcome it, the material will be a solid. So in solids, we can see that the particles are packed closely together without any translational or rotational motion. The only freedom they have is vibrational, which means they're going to wiggle and waggle back and forth. Solids cannot flow, liquids do. So do gases. Solids are not compressible. Liquids are. They are not, but gases are. So since gases are empty space, they're compressible and flow. Liquids have higher densities than gases, but are incompressible because the particles are indeed still in contact with one another. They have an indefinite shape, in other words, they can flow, because the limited translational freedom of the particles allows them to move around enough to get to the container walls. Liquids can flow, but they do have a definite volume. Because the attractive forces between the molecules are fixed, changing the material state requires changing the amount of kinetic energy the particles have, or limiting their freedom if we're moving the opposite directions. When solids melt, they're heated because the particles gain enough kinetic energy to overcome the attractive forces and begin to flow past each other. When liquids boil and when heated, those particles gain enough kinetic energy to overcome attractive forces and literally escape from liquid phase to gaseous phase. The higher you raise the temperature, the more freedom of motion, the more kinetic energy the particles will have. Gases can be condensed, gas back to liquid, by decreasing the temperature. Decreasing its kinetic energy and making them move more slowly will cause the gases to liquefy. We can also increase pressure. We increase pressure by placing it into a smaller volume. If we pack the molecules so close, the gases will compress and form a liquid. When a solid is heated, it forms a liquid. If a liquid is continued to heat, it will form a gas. Solids will melt, liquids will vaporize. Gases, if we cool them, go back to the liquid phase, condensation. Liquids, if we cool them, will form a solid, removing kinetic energy. This is called freezing. So we're just looking at phase changes along the way. The strength of the attractions between the particles of a substance determines its state. At room temperature, moderate to strong attractive forces result in materials being solid or liquids. The stronger the attractive forces are, the higher the boiling point of the liquid will be. And the melting point of the solid will also be higher. We'll see that there are other influences to the melting point as well, but it all has to do with attractive forces. The more energy I have to put in, the higher the boiling point. The more energy I put in, the higher the melting point. So why are molecules attracted to each other? Those intermolecular attractions are due to attractive forces between the opposite charges. We mentioned that a polar molecule has an area of a positive and an area of a negative. That ions can either be positive or negative. Intermolecular attractions are all about opposite charges. Hydrogen bonding is especially strong in a polar molecule, such as water, the hydrogen of one end being attracted to the oxygen of the other end. Even nonpolar molecules can have temporary charges as the nuclei shift the electron density around them. The larger the charge, the larger that dipole moment, the stronger the attraction. The closer together the atoms are, the stronger the attraction. If we have a big distance, a long distance between molecules, that creates a weaker attraction. When the attractive forces are small relative to the bonding forces between atoms, we see smaller charges, and overcoming larger distances creates a weaker bond as well. So the stronger the attractions between the atoms or molecules, the more energy it takes to separate them. Boiling a liquid requires we add energy to overcome attractions, not to break covalent bonds, but to overcome intermolecular attractions. Intermolecular, between molecules, not within a molecule, but between them. The higher the normal boiling point of a liquid, the stronger the intermolecular attraction. Higher boiling points due to strong between the particle attractive forces.